So just a recap of where we are. We have cleared away the type of wear and the equation, the Archer equation. Alright, let's talk about the wear testing now. Okay, so the wear testing, let's take a look on this video and you should know a bit. So you may wonder what the hell is going on, right? So in fact, right, maybe I should find some place to paste the picture. Give me a while. This is the point. This is the material that you want to test. Okay, the amount of wear. This is the hard material, or extended. Is the hardest material that they could find. So you rub this so-called your soft material against this hard material, and see what type of debris will it come out of there. Okay, and therefore it's moving all along. Okay, the wearing part. So this is why. Yeah, so it's called a pin on this wear testing. Alright, it's a method of categorizing coefficient of friction, frictional force, and rate of wear, or between two materials. So all in all, it can also test for friction and etc. Alright, so take note there is a pin on this. Okay, and therefore when you come to the slides over here right now, alright, the pin on this is also come over here, the pin or rod test. Alright, so this is the pin, and this is this. Okay, so this is this is another scenario. Instead of this thing moving, this is rotating. Alright, so this is rotating, and we see how much wear is over here. Maybe I should use a different color. How much wear is over here at this side, this contact surface. Okay, and therefore what you should remember is this equation. Okay, this is exactly the same as this, just that they write in terms of VI and KI, but KI is equals to KH. Alright, KH is this one. This is the constant. Alright, and in fact this KI, they call it the wear rate coefficient. Alright, and it is in terms of meter cube per Newton meter. Okay, the Newton meter is, I think, is the hardness thing, and nonetheless I don't know, so you cancel each other, you get meter square over Newton. Alright, so it's the amount of area per force. It's a weight formula, but anyway, you should take note of that. Okay, and the SI unit also. Alright, so it's a meter square per Newton, but you should know that it comes from this thing. Alright, and I don't need to explain the rest, because still the same thing is the same thing with the Archer's wear equation. V is equals to volume of the wear debris. Okay, so the amount of volume is still determined by the amount of sliding distance you're talking about, and the weight of the material, or the loading, they call it the loading. Alright, and H is the hardness of this thing. Alright, they are talking about this hardness of this material, this pin. Okay, so all in all, you should take note of this equation. Includes the important rate there. Note that this is still called the normal forces. Alright, and nonetheless, this is also can record the specific wear rate. Alright, or the wear rate coefficient. So there's a few names to it. Okay, that you should take note. So there is a name specific wear rate or wear rate coefficient. So please take note of that. You remember a few videos ago we touched on the friction, right? The friction over here is still talking about the stress maximum is equals to the force over area, alright? So if you remember, force over area is equals to stress. So it's the same thing over here. Instead of force, they write as the normal load. Okay, it's the U strength of the material, the U stress of the material. Okay, so so using this equation, they actually sub it into this equation. Alright, let's take a look on what is the magic behind there. Alright, and see how it goes. The surface contact, alright, there is a page 20. Alright, then there is this H is equals to 6K is equals to 3SY. Let's take a look. Seriously, I don't know what the hell is going on. Okay, so if let's say 3SY, I know where it comes from because of this equation. Alright, so how I get this thing, I don't know what the hell. But for example, right, so if let's say I have this equation, or this equation is our first part, alright, this Archer's wear equation, And if I were to sub in my W as this thing, so this means that I'm going to pull it out. Alright, so therefore this will imply that I will have KLASY, alright, H. Okay, so if I were to bring this A down, because this is equals to V, I will have V over A as equals to KLSY over H, okay, which is this part. But I don't know where the hell is the 3 comes from. So over here they say it's proportional. So this I would imply that stress max is proportional to 3SY. Alright, also is equals to WA. So this is why if that's the case, then if I were to sub in my W, so my W will be equals to 3, the U strength of the material. They call it the U pressure, U stress, U stress, alright, U pressure, alright, U pressure, okay, in any of the case lah, alright, times the area, okay, so I will have KL, alright, 3 U stress area, alright, times H. And if I were to rearrange, I bring the A down, I'll have V over A as equals to KL SYH times 3. Alright, hopefully you kind of clear what I mean. So we have derived somewhat about this equation, alright, and we don't know what is A. Alright, V over A is equals to some A. I don't know whether is it the impression radius. Alright, oh yeah, it's a hemisphere with radius A. Give me a while. So I would think that the A is the apparatus, so these are the surface contact. Alright, so at this particular surface, alright, there is a certain form of curvature over here. So this curvature is somewhat half hemisphere, half the sphere, alright, and therefore this radius is called the A. I think, I don't know, I'll leave you to think about it. I will check already. But nonetheless, we have derived this thing. So how do we get this dude over here then? Alright, is that so? Right, in any of the case, if I were to sub in my H, alright, my H can be equals to 6 here, can be equals to 3SY. Alright, so if I sub in this, I can cancel. Alright, then my V over A is equals to KL. Alright, then I also don't know what the hell is going on. But nonetheless, they want our equation to be in terms of H. Okay, so I think maybe I should change these things a little bit. Alright, let's see. So SY is in terms of K, so maybe I should change to K. Okay, I somewhat solve it. Okay, so this equation, alright, I actually switch. I bring the H up, I bring the V down. Alright, and this explains why I have this thing over here. So my V was at first was here, right? So I bring it down, and then the H I'll bring it up. So and then after over here, my V, I know that my volume of the amount of, this is the volume of the debris being wear off, right? So the equation is A is equals to V over A, right? So AA is equals to V. So I sub in my AA over here. Okay, hopefully this is pretty clear. So once I sub in this equation already, alright, then I sub in back my W, which is the one that we have solved for it just now. Alright, where we see, it seems that our W is 3SYA, okay, for some don't know what the hell reason, okay, but nonetheless, once we sub it in, we get this thing over here, okay, so therefore, once we get this already, in fact this is A lah, okay, so over here you know that A is, L is equals to 2A, and therefore A is equals to L over 2. So I sub in my A as equals to L over 2, and this is why you can see that there is a L over 2 over here. Alright, so nonetheless, first I rearrange this thing, alright, in case you don't know how I'm talking. Second, alright, I change my V to AA. Okay. Third, I change my A into L over 2. Okay. Then I start to cancel, I should reach this. Okay. And this is how you find your hardness value, 6KSY. I don't know whether is this important. I don't think it's important. Okay, but something for you to know lah. In the future you may need it. Wonder what is this equation related to this? I don't even know anything about all this. Okay, I don't even know that this is the amount of volume being displaced. This H, I think is the also never say much. So I think it's the hardness of the material. Okay, yeah, hardness of the soft material. Okay, I don't know why if the K, yeah, so if the K decreases is a mount wear. A mount wear have a K of 10 minus 8. Also meaning if you are very lousy wear, then it's about this thing. If you are very severe wear, then it's K equals to 10 minus 2. So does this imply that the lower the K, alright, the the less harder of the material? So because the K is proportional to the hardness of the material, so if K is lower, then this means that the material is softer, right? So if this material is softer, then you'll have lesser wear. Is that the meaning of that? I don't know. That's something for you to find out also. Alright. All in all, you should take note of is the K value, mild and severe. So maybe the question may give you the thing is under a mild wear. So if it's a mild wear, then you should know K is equals to this value. You should memorize in your heart, I think. You never say you need to memorize, but I think in case that you may need to check it out, then at least there. Alright. So there's a different values on there. Alright, mild steel for different K value, I think. Alright, so you can check it out if you're free. Alright, the different materials, alright, for different K values. For lubricated conditions, the power value may be doubled, 10 minus 5 to 10 minus 10. Alright, so if this is 10 minus 5, it will change to 10 minus 10. Alright, if you have a lubrication, so the K value decreases. Alright, so I think this is the meaning of that. So yeah, I know. Yeah, lor. So you need to know that the volume of material worn away is V, or the volume of material worn away is equals to K times the load times the L, sliding distance, where your K is the Ki. Ki is equals to the K constant divided by H, the hardness of the material. Okay, this is the Pi actually. So nonetheless, this can be called the load. This can also call the bearing pressure, or it depends on how you say that. Okay, where the K is the wear factor. Alright, where you can call the wear factor, you can call the specific wear rate, alright, or you can call it the wear rate coefficient. So a lot of names in there. But hopefully I think you kind of understand it clearly what the hell is going on. Alright, so the important thing that you should take home is this equation. Okay, the amount of volume and the K value, and this K value you should take note of it, and this K value should be K divided by H, the hardness of the material. Or you should take note of all these things, little stuff, and nonetheless also this type of wear rate. Alright, so the don't know thing is that if the K is lower, this means that material is softer. So material is softer, then this means that it's lower wearing. Yeah, that's the thing. So this means that tofu has lower wear rate than metal. Is it? Because I think if it's lower wear rate, then this means that if you scrap upon this thing, this piece is being sliced off. Your tofu is being sliced into half. So it's lower shearing, is it? I don't know. So yeah, I'll leave you to think about it lah. So yeah, I think that's all for the wearing part. So in the next video we'll talk about a bit about the lubrication, and I don't know whether is it important. You give me a while. No need lah. I think I can just put it in this video straight away. So when two surfaces slide against each other, or under high pressure, please take note high pressure, without potential layers, the friction and wear will be high. So the friction and wear comes together as a family. Alright, so you need a lubrication and reduce the wear factor. So therefore, over here, if you this is the wear coefficient, the K. Okay, take note is 1 over K. Alright, so it's 1 over K. So this means that if you change back to K, is actually 10 to the power of 5. Alright, so the higher the K value, the better? The harder the material it is lah, I think. Alright, so actually this is quite why wear coefficient is K to the power of -1. So just now as I say, right, if you were to have times 2, alright, as it says, if you put in the lubrication, alright, the lubrication, the power value may be double. Alright, so 10 minus 5. So this K is in terms of K minus 1. Like seriously. So 1 over k is equals to 10 minus 10. If k then is equals to 10 over 10, then fucking big, you know. So this means that material is very hard. I don't know. There's a relationship in there. So take note of the coefficient. I think it will be very important to know. Alright, in like meter square per Newton. So this is equals to k. Alright. So if it's inverse k, then this means that the Newton per meter square. Alright, this amount of forces or amount of stresses. Alright. So inverse k is actually a stress. So the lower your k, inverse k, the better it is. It's because the lower the forces per area. So I think you get the meaning of that already. So the lower the inverse of the k, why the lower the amount of forces. So you want to actually increase the lubrication so that the wear is significantly lowered. Alright, because if you think about it, meter square per Newton. So if the k over here is larger, this means that your Newton over here is lower. Alright. So for example, 30 divided by 0.00001, the force is very small, so you'll get a very large number k. So this means that the higher the k value, alright, the better it is. Alright, at least something we can deduce about it. Alright, higher the k value, better it is. But lower the k inverse, the better it is. So be careful of these two links. Alright, higher the k value and the inverse k value. Okay, higher k, better. Lower k inverse, better. Alright, take note of that. So coming back to the tofu case, alright, so if the tofu k value is high, this means that the tofu is able to slide off the material easily. Alright, so the amount of forces trying to wear it away is less easily than metal, because the tofu has higher k value, which means that the amount of Newton per area is very small. I don't know what I'm talking about, at least you know what I mean. So just take note of the higher the k value, the better. The lower the k inverse value, the better of this relationship. Alright, so just need to know that. And take note that your metal reinforced this thing over here is the best. Alright, it's a mixture. It consists of mixture of hard and strong materials. One component provides some inherent strength, another one provides low shear stress. Alright, so the lower the k inverse, the better. Alright, so I think it's quite informative for me. So I think that's all. Yeah. So I think see you soon for other stuff. Clear away the equations already. The equation is the most troublesome part, so I think we have somewhat clear away. So the rest is talking about the surface engineering process, is more on theory part. So if I have free time, then I'll just continue with it. So I shall see you soon.